we have introduced the concept of reservoir, we have introduced the concept of thermodynamic potentials and how are they arrived at, and we have already defined previously in week 3 also we have defined like G and F, but how are they coming and how are they related and what is this conjugate relationship that we are talking about, we have explained them. Now you have system and reservoir, right? We have talked about system and reservoir. If you remember the previous lecture, we talked about that if I have Helmholtz free energy minimum principle, that basically means that F, which is a function of now T, right? F is a function of T and V and N, and dF has to be equal to 0 and d2f has to be greater than 0. So it is the Helmholtz free energy minimum principle. So instead of using a energy minimum principle or entropy maximization principle where we require the equations of state, now if I talk about a system in contact with the reservoir is very large, then basically we can, and it is a thermal reservoir, then we use Helmholtz free energy, and in case of Helmholtz free energy we have seen that dF has to be equal to 0, right? That is an extremum condition, and d2f is greater than 0, right? We basically have seen that the delta f has to be less than or equal to 0. Delta f equal to 0 when the process is reversible. But if you now look at df in terms of d, which is the exact differential of f, then df has to be equal to 0 for extremum, and d2f has to be greater than 0 for this extremum to be a minimum, right? d2f has to be greater than 0. Now think of this. This is another very interesting thing that comes in, which follows, is that system plus reservoir. That system plus reservoir, and this is a thermal reservoir, right? When we are talking about a reservoir in case of Helmholtz free energy, because where we have replaced S with its conjugate variable T, then system plus thermal reservoir, if you take together, then basically they together form an adiabatically isolated system, right? Which does not permit, exchange of energy with the surroundings, right? So system plus reservoir, so reservoir is your thermal reservoir, so system plus thermal reservoir together is an adiabatically isolated system, right, which does not permit any exchange of heat with the surrounding, right? So you can think of this as an adiabatically isolated system. So basically what we are trying to say, you have system and then you have a reservoir. Let me make the system smaller compared to the reservoir. So this is your system and this is your reservoir. And say the reservoir has a temperature Tr and your system has a temperature T. So what we are basically telling, the constraint here is that if the system is in contact with the reservoir, then T equal to Tr, right? So T takes the temperature of the reservoir, right? So T has become equal to Tr. I should write T equal to Tr, right? And Tr is the temperature of the reservoir. Now if you look at this entire stuff, so this basically, this entire system is a adiabatically isolated, right, system, right? It is adiabatically isolated from the rest of the universe, right? It is basically adiabatically isolated from the rest of the universe. So if it is so, it does not permit any exchange of heat here. So it is not Q, this is not permitted, right? So there is no exchange of heat. In that case, if you think of system plus reservoir as your adiabatically isolated system, then if you look at the definition of W here is minus of delta U plus U. Now this follows from, so if you think of the W is the work done by the system, then it is nothing but equal to minus of delta U plus U, right? Which is basically, U is the change in internal energy of the system and UR is the change in internal energy of the reservoir. Now you have like minus delta U minus delta UR. So minus delta, so basically delta U plus delta UR plus W basically will give you either equal to, will be equal to 0. So now if that is so, one very interesting thing that comes in here is that you have delta UR, right? Delta UR is a change in internal energy of the reservoir, and assume a reversible process. So delta UR is nothing but TR delta SR, right? So it is TR delta SR, right? Delta SR is the change in entropy of the reservoir. So we can write minus delta U minus TR delta SR. Now we have from second law that delta S plus delta SR has to be greater than or equal to 0. Right? For a reversible process, if only reversible process is taking place, delta S plus delta SR equal to 0, right? This plus this equal to 0. Equality condition happens. So that means delta SR is nothing but minus delta S. So now think of this work as reversible work. Then we can write W reversible is minus delta U, right? Minus delta U plus TR delta S, where delta S is the change in entropy within the system, right? Not within the reservoir, but within the system. So minus delta U plus TR delta S. Now, TR and T are same. So we can write minus of delta U minus T delta S. Now delta U minus T delta is nothing but minus of delta F. So the drop W reversible, that is the maximum work that is done, the W reversible is equal to negative of the change in Helmholtz free energy, right? And as we know that W irreversible, that the work done by if the processes are irreversible, then the work done the network done by an irreversible process is always less than the work that you can get or obtain from a reversible process. And for a reversible process, you have the maximum work, and that maximum work is basically equal to negative of the change in Helmholtz free energies, right? Helmholtz free energy. This is also basically called maximum work principle, right? So maximum work that is derived is the negative of the Helmholtz free energy. So Helmholtz free energy in some way defines the maximum work that can be obtained, right? And the maximum work that can be obtained is always through a reversible process, right? Irreversible process, the amount of work that can be obtained is always less than that of the reversible process, right? That we have already discussed in the purview of second law, right? Okay, now let us look at another means in general in materials science we deal with the changing Gibbs free energy, right? We will look at, and as you see later, that when we look at solution thermodynamics and we look at the phase equilibria and phase diagrams and their relation to phase equilibria, we will always consider Gibbs free energy, right? Why Gibbs free energy? Because we are assuming, so why Gibbs free energy is because when we have this multi-component, multi-phase systems and we are looking at the equality of chemical potential, we often want to use a thermal reservoir as well as a mechanical reservoir. So that means if I think of thermal and mechanical reservoir, we have T equals to TR and P equals to PR. That means the pressure of the system. So T is T system, right? T system is equal to the temperature of the reservoir, and P system equals to temperature pressure of the reservoir. So basically a system that is in contact with the thermal reservoir and the wall is flexible so that the volume adjusts such that P also is equal to P, right? So basically you have a system that is in contact with the thermal reservoir, but now the wall of the system with the reservoir is flexible so that the volume adjusts in such a way that the pressures are also, the pressure inside the system is equal to the pressure of the reservoir, right? Now again let us look at this idea that you have system plus reservoir, and the total, so system plus reservoir itself is like an isolated system, and in that case the change in U plus UR is the total, the total change in energy, right? The energy is constant, right? Energy is constant. So the total energy tell you U plus UR for that system equal to constant. So this system basically is nothing but, this isolated system is nothing but system plus reservoir, and the reservoir is a thermal as well as a pressure reservoir, right? Thermal as well as a mechanical reservoir, you can think of, right? Now if that is so, then if this is so, then immediately this implies this, right? Delta U plus UR is equal to 0. Similarly, the total volume, if I think of the total volume, V plus VR, right? V plus VR, that is also going to be constant. So as a result, delta V plus VR equal to 0, right? So delta V plus VR equal to 0, delta U plus UR equal to 0. That means delta U is equal to minus delta UR. Again, delta V is minus delta VR. However, delta VR and delta UR, because reservoir is assumed to be infinite compared to the size of the system. So always we assume that the reservoir's size or the size of the reservoirs is much larger. That means it is almost infinite compared to the size of the system. Reservoir is so huge that it is infinite compared to the size of the system. So in such a case, delta VR and delta UR are going to be, even though there is, see, if there is a change in internal energy of the system, there is definitely a change in this. See this relation, we have already shown that the delta U is going to be minus of delta UR, or basically you can tell delta UR is going to be equal to minus delta U. That means if there is a change in internal energy of the system, then there is also a change in internal energy of the reservoir. However, the reservoir is so huge that the temperature of the reservoir remains TR, even though there is a very infinitesimal change in the internal energy of the reservoir, right? So del UR equals to minus delta U, but delta UR and delta VR, right? Delta VR and delta UR are infinitesimal and neglected due to the infinite size of the reservoir. This is a very important point, that delta VR and delta UR, although they are there, but they are infinitesimal and they are neglected because of the infinite size of the reservoir, right? Although this relation is indeed true, that delta U equals minus delta UR or delta V equals minus delta VR. So these are true, but delta UR and delta VR are very small, right? So delta UR, which is minus delta U, is negligible, right? It is negligible, and you can call it like 0. Delta VR also is negligible. Thus, PR and TR, that is the pressure of the reservoir as well as the temperature of the reservoir, are constant. But from second law, you tell that delta S of the system and delta S of the reservoir have to be greater than or equal to 0. Now, delta S reservoir is nothing but delta UR by TR, and also you have also change in volume of the reservoir, right? So you have PR is the pressure in the reservoir, into delta VR, because there is a change in volume because the wall is flexible between the system and the reservoir. So you have PR delta VR and delta UR by TR. So you have delta SR, which is delta U plus P delta V, right? So delta SR, which is delta UR by TR plus PR delta VR by TR, which is basically delta UR is nothing but minus delta U, right? Minus delta U by TR. And this will be PR delta V, because delta VR is minus of delta V. So you have a minus sign. So therefore so from this relation you can see you are replacing delta SR with this term. Okay, so then it becomes, I take delta common, it becomes U minus TRS plus PRV is less than or equal to 0. Now G, because TR equal to T, since TR equals to T, right, and PR equals to P, thermal and mechanical equilibrium, then G is U minus TRS plus PRV, which is U minus TS plus PV, right? And U minus TRS plus PRV is nothing but G, right? So, which is U minus TS plus PV, and instead of T I am writing TR, and instead of P I am writing PR, because indeed the system is taking the temperature of the reservoir and system is taking the pressure of the pressure inside the reservoir, right? So basically the at mechanical equilibrium means indicates that the pressure of the reservoir and the pressure of the system is the same, right? And the pressure of the reservoir is held constant because reservoir is infinite compared to the system, right? I am repeating several times to emphasize these very important points. And therefore, we can write directly from this relation which comes from the second law. Remember, this is coming, all of these are coming from the second law, right? Second law tells this. And delta SR I have written in terms of minus change in internal energy of the system and change in volume of the system, right? There are two quantities. Delta SR is expressed in terms of change in internal energy as well as change in volume. And also we have made sure that we see that we have PR here and we have TR here, because the PR and TR are not only the temperature of the reservoir and pressure of the reservoir, they are also temperature and pressure of the system at thermal and mechanical equilibrium respectively. So as a result, we can directly write delta G less than equal to 0. Again, it gives you the Gibbs free energy minimum principle, right? It gives you the values of the the unconstrained internal parameters that they will assume is basically those which will minimize the free energy, and the free energy change is less than, means so the extremization conditions, if I write in terms of differential form, is dg equal to 0 and d2g is positive. And here what we are telling is delta G, that is not an infinite small but a macroscopic change, the delta G has to be either equal to 0 or less than 0. Now we want to discuss, so basically we have now discussed these different thermodynamic potentials like Helmholtz free energy. Even enthalpy can be is one thermodynamic potential. Enthalpy is one thermodynamic potential. Again related to the to U and S and V. So via the Legendre transform, where we are basically replacing V by P. So enthalpy, Helmholtz free energy, Gibbs free energy. Okay, so we have defined at least these three thermodynamic potentials using the conjugate relations and or using the conjugate variables. Now comes one very important consequence of exact differential. So these are called Maxwell relations. Now, if you remember, we discussed already that dz, if it is an exact differential, is m dx plus n dy, and where m is basically del z del x, and again if I am using partial derivative, it implies that del z del x with constant y, and n equals to del z del y at constant z. By the way, Maxwell relations, you will see that are basically very useful to derive many important thermodynamic relations between directly measurable quantities in thermodynamics like temperature, pressure, volume, thermal expansion coefficient, heat capacities, and the indirectly measurable quantities such as energies, right? Different energies or different thermodynamic potentials, right? So you have this, and we have also told that the property of exact differential is that del m del y should be equals to del n del x. That means the second derivative is where we are looking at. So we are telling del 2z del y del x is the same as del 2z del x del y. That means the change in order of differentiation does not really matter if you are dealing with an exact differential. That means del 2z del y del x, see, the order is different, right? First we are doing del z, if I am looking at, we are finding del z del x, and then we are differentiating with respect to y in this case. Here it is first with respect to y and then with respect to x. But that does not matter. The order does not matter as long as dz is an exact differential. And we know that all state functions in thermodynamics are exact differentials. No. So then we can basically replace them. So we can write like du as tds minus pdv plus mu dm. Remember, T is del u del s, P is minus p is del u del v and mu is del u del n. Similarly, I can write df. Now, in the case of f, we have to use t, right? We are, instead of using s, we are using t. So, it is minus s dt minus p dv plus mu v. For h, it is t ds plus v dp plus mu v, right? Here, what we are basically replacing? We are replacing v by its conjugate, that is p, right? So, basically, we have t ds plus v dp and mu dn. And dg, where we are replacing s with t and v with p, then basically becomes minus s dt plus v dp plus mu v. So, these are 4 exact differential relations, right? In this, these are the common thermodynamic potentials that are used in all thermodynamic analysis of simple systems, and you have du, df, dh and dg, right? Now, you see a very interesting consequence, that you have du as a function of s and v. Now, we are just keeping n constant for time being. We are not n is assumed to be constant. See, all of them have mu dn, mu dn, mu dn and mu dn. So, now it becomes del 2u del s del v n. Now, as you can see, is because again this is coming from this definition of exact differential. So, del 2u del s del v n is same as del 2u del v del s n. The order does not matter. So, as a result, now you see, in one case it is del u del s and then del u del v. Another case it is, so this implies is basically, if I tell that del v is there, so del t del v. So, here we are using t. T is what? T is nothing but del u del s. T is nothing but del u del s. So, what we are basically telling is del 2u del v del s is basically del v of del u del s, and del u del s is nothing but t, which is equal to del t del v. On the other hand, del 2u del s del v is nothing but del s of del u del v del u del v is minus p, so this is minus del p. So, this is what we have written, del t del v s n is equals to minus del p del s v n, right? Now, if we look at the Helmholtz free energy, we have t as one of the variables, t and v, right? So, del 2f del t del v is equal to del 2f del v del t. Again, that gives you del s del v is equals to del p del t. How? Because del f by, if you think of this, del f by del t equals to minus s. Del f by del t equal to minus s, and del f by del v equals to minus p. So, you have, if you again look at the sequence, so you have del f del v is basically equal to minus p. So, this becomes minus del p del t, and this becomes minus del s del v, and so minus minus cancels out, with both become plus. So, basically you have this relation del s del v t equal to del p del t v, right? Del p del t v, and also r is fixed, right? As I am telling that I have written n, but you can neglect this n, right? N is fixed because we are not doing anything with n, and in both sides. So, you have del s del v and del p del t equality, again coming from this equality of the second derivatives, right? The equality of the second derivatives is giving you equality, some useful relation between so this useful relation is coming because del s means you are replacing the, so the order does not matter, but del f del t we are replacing by minus s, and then you are basically replacing del f del v by p. So, you get another useful relation. So, all these relations are coming by equating the second derivatives and telling that the order does not matter, As a result, if the order does not matter, I can basically tell that if I do del V of del U del S or del S of del U del V, they are the same, and del U del V we are replacing by minus P, and del U del S we are replacing by T. So we are getting these very useful relations, right? So again, for example, if it is H, you have S and P, so you can write del 2H del S del P equals to del 2H del P del S, which gives you del T del P. See, it gives you del T del P as a, because you have del H del S is equal to T, right? So del H del S is equal to T. So del T by del P equals to del H by del P. So del H by del P here is equal to V. So you are using, which is basically del V by del S, right? Del V by del S, right? Del H del P is V, and del S of del H del P is basically del V del S. So del V del S equals to del T del P. Okay, so there are various ways to remember these relations. There is something called thermodynamic square. I will not get into that, but what I want to tell is that it gives you Maxwell relations. Although it initially looks a bit tedious, you will see that these Maxwell relations can be used. Okay, this can be used to derive many useful relations between the indirectly measurable quantities and directly measurable quantities. Again, we have del 2G del T del P equals to del 2G del P del T, which tells you minus del S del P equals to del V del T. Again, another useful relation. Why are these useful relations? We can immediately see here, for example, del V del T has a relation with alpha, right? Del S del T has a relation with Cp, right? So because dH equals to TdS, say at constant pressure, for example, we know at constant pressure dH equals to TdS equals to Cp dt. So del S del T P is Cp by T. We have already seen that. Then similarly, del S del T V equals to Cv by T, because du equals to TdS, right, at constant volume, which is equal to Cv dt, and so therefore del S del T V equals to Cv by T, right? So, and you can see here that we have got these other relations here. So now if we look at this, del 2H del S square, for example, now del 2H del S square, okay, at constant pressure is basically double differentiating enthalpy with respect to entropy. What we get is del T del S, because del H del S is equal to T, right? Del H del S, because dH equal to TdS, right? So del TdS plus VdP plus mu dm. So TdS, so del H del S with at constant pressure, del H del S at constant pressure, right, is equals to del H del S at constant pressure is equal to T, right? So now you are using T, so del T del S P. Now del T del S P is nothing but inverse of del S del T. So you get immediately a measurable quantity. Del S del T is nothing but Cp by T at constant pressure, right? So this becomes, yeah. So now you have del 2H del S del P, which is del T del Ps, right? Again, we are using del H del P. Del H del P, if you write, so you have VdP. So del H del P is V, right? So you have del 2H del S del P, and we are doing del H del S. So basically we are writing this way, del H del S, and so in fact I should have written del 2H del P del S, but it does not matter, right? The order does not matter. So del 2H del S del P is del 2H del S del P del S, which is basically del T del P at constant entropy, right? Again, del 2H del P squared, if I do, which is nothing but del H del P, which is V, and so this becomes del V del P at constant S, right? Now, if you look at this, now these three relations give you an example. See, I want to give you an example that how these relations of second derivatives and the relations between the second derivatives and first derivatives, which gives you, from the second derivatives we get a very useful relation between the first derivatives, which relates temperature and pressure change at constant entropy, or volume change with pressure at constant entropy, or volume or temperature change with entropy at constant pressure, and all of these are related to some useful quantities like Cp, Cv, or alpha, or beta. Here we call it kappa T and kappa S. Kappa T basically is
isothermal compressibility, that is at constant temperature, which we have defined previously as minus 1 by V del P at constant temperature. We can also think of adiabatic compressibility where entropy is constant, so Ks or kappa S, which is minus 1 by V del P S. So you have del V del P T here, you have del V del P S here. Now if I tell you, find the relation between Kt and kappa T and kappa S, that is isothermal compressibility and adiabatic compressibility, you can use these relations. How? You see, first of all, if I want to use these relations, we have to use some properties of derivatives. So one property that we immediately can see is that del x del y z can be written as del x del w z and del w del y z, right? It is basically, we have some variable called w, so del x del y is replaced by del x del w. So there is another variable w, which is again a function of say y. So we are telling del x del w and it is also a function of, so x is a function of w and x is also a function of y. So I am telling that del x del y is nothing but del x del w del y, right? This is very classic chain rule. Now this also means that del x del y we can also write as minus del z del y x or del x del z y, or we can also write it as minus del z del y x, and this is del z del x y minus 1, right? Or minus 1, right? So it is inverse. So basically what we are telling is del x del z y is nothing but 1 by del z del x y, or equal to del z del x del z del x y is equal to minus. Now this relation is quite interesting, right? It's a cyclic relation, a chain rule. How does it come? So let us look at this. We have already discussed that, but again, just to recollect, dz, if z is a function of x and y, one can quickly write that dz equals to del z del x. Again, just writing del z del x means that y is constant, right? Del z del x means y is constant dx plus. So dz again is a exact differential. So this will be del z del y. It's fixed, and this is b. Now put dz equal to 0. So what you get is del z del x y dx equal to minus del z del y x dy, or you can write del z del x y del x del y, right? Sorry, del x del y. So del z del x y, del x del y. So what I am doing here, you have dx, here we have dy. I am doing differentiating x with respect to y, keeping z constant. Differentiating x with respect to y. Sorry. Keeping z constant. And because I am just taking dy here, so del x del y is z, and this is minus del z del y x, right? or if I take this also here, so it will be inverse of del z del y x. If I take this guy to the left hand side, then del z del y x will be coming to the denominator, right? 1 by del z del y x, which is basically nothing but del y del z x, right? So this becomes equal to, so this is minus 1, and this becomes c del z del x y del x del y z fixed and del y del z x fixed, which is equal to minus 1. See, del z del x del y del z, right? This is like del z del x del y del z, and it's like a cyclic chain rule. And we have del z del x, when we are writing y fixed, del x del y z fixed, del y del z x fixed equal to minus 1. See, this is something that we have used in the previous lecture also. So I am just, and we have proved it in the first week itself, in the first week or second week, and this is something that we will continue to use. So many of this, remember, one of the means when you want to find useful relations, there is a little bit of algebraic manipulation involved, right? It's a little bit of mathematical jugglery involved, and that basically centers around the only logic or that you have to use, or only math that you have to use, is the properties of partial differentials, right? And the properties of exact differentials or inexact differentials. So basically, a little bit of understanding of partial derivatives and the relations between them will be very useful for deriving very useful important relations in thermodynamics. However, note that when you are deriving any relation, remember that whatever relation you derive, it is always important to derive relations in a way so that you can relate, or the relations should be such that you can involve several measurable quantities. Then only you have the directly measurable quantities. For example, temperature is a directly measurable quantity using a thermometer, or pressure is a directly measurable quantity using a barometer. Measuring tape can measure volume, right? Volume is a directly measurable quantity. Now think of Cp and Cv, like heat capacity at constant pressure or constant volume. These can be measured, we have already discussed, by calorimetry. And then you have alpha, which can be measured using that is a volume expansion coefficient, means thermal expansion coefficient, means change in volume with respect to temperature. Again, we can be related to the linear the thermal expansion coefficient, and this can be measured using something like dilatometry. And then you have beta, which is beta or kappa T, kappa S. These are like isothermal compressibility and adiabatic compressibility, which can also be measured, right? So now, if you have this type of relations, what we have is, now we have basically the relation between, we want to find a relation between kappa T, kappa S and all these derivatives. So if I use these relations now, you see, so again, following this relation that we have, del z del x del y del z equal to minus 1, we can write del x del y z is minus del z del y fixed x times del z del x inverse fixed y. So basically what we are now trying to replace is t. So basically my x is t, so z is basically s. So s is a function of t comma p is what we are considering. Now if that is so, you have del t del p, which is we at fixed s, which is nothing but del f minus of del s del p times del s del t inverse, right? We are just using the cyclic chain rule. So we have this relation. Now as you can see, del s del p, what is del s del p? If you remember, or if you do not also, I'll just remind you. So let us look at del s del p. So we have found this. So del s del p is nothing but del v del t, which is nothing but, see, alpha is 1 by V del V del T P. Now, therefore, del V del T P is nothing but V alpha. So, V alpha. So, del S del P minus of del S del P T is equal to V alpha. So, now using that relation, minus of del S del P T is nothing but V alpha. Del S del T P is Cp by T, but this is del S del T P inverse, so this is T by Cp. So, this becomes T V alpha by Cp. Now, you have del S del Pt, which is minus del V del Tp, which is minus V alpha. Del S del Tp is Cp by T. Now, you can see that you have Cp by T, and another relation, if Z is a function of x, y and w, we can also write dz equals to del Z del x y comma w, and del Z del y x comma w, and del Z w x comma y, and now we are telling dw equal to 0. So, if dw equal to 0, then we can write this as dz equals to del Z del x y comma w dx, del Z del y x comma w dy, or if I can differentiate again with respect to y, basically I am dividing both sides by dy, I get del Z del y w equals to del Z del x y w del x del y w plus del Z del y x, right. This is some relation that also we are very familiar with and we can easily derive. Now, if you use all this relation and then I write volume, so this is the point that I am trying to say. Whenever we measure, we first want to find out what is the most useful relation that we should use. So, here for example, to find the relation between isothermal compressibility and adiabatic compressibility, we are using the relation between V, and V is related to temperature, pressure and entropy. Right, we are writing V as a function of temperature, pressure and entropy, right, and we are now telling isoentropic, that means entropy is fixed. So, that means I am going to directly use this relation. Here W is fixed, right, here W is fixed. So, we are going to use this relation, and so instead of W here we are talking about S fixed, right, S fixed. So, if I use this, now you have del V del P S equals to del V del T P del T del Ps plus del V del Pt, right. So, now del V del Ps basically is 1 by V del V del Ps is minus 1 by V del V del Ps is basically your, so if you remember, minus 1 by V del P S was defined as kappa, right. So, so therefore, this is nothing but minus, so this is nothing but minus V ks. Now, del V del T P already we know is V alpha. Then you have del T del P S. Now, what is del T del P S? Again, what is del T del Ps? We can have del T del Ps equal to, we have done this, del T del Ps is equals to T V alpha by Cp, right. We have just now we derived it. So, we will use T V alpha by Cp. So, you have T V alpha by Cp here. So, you have T V alpha by Cp and this is V alpha. So, and you have here Vks. Now, if you see, and here del V del Pt is nothing but minus V kappa T, which is, now if you do this and if you rearrange, so what do you get? Minus Vks kappa S equals to V alpha times del T del Ps, which we have got as T V alpha by Cp. V alpha T V alpha by Cp minus V kappa, which is isothermal. So, this is isothermal compressibility, this is adiabatic compressibility. You can take out one of the V's, right, you can take out one of the V's. Now, so what happens is kappa T minus kappa S is basically going to be TV you have 2 alphas, right? TV alpha squared, TV alpha squared by Cp. Now you see these two relations, which again can be measured maybe with some difficulty, are related to some very easily measurable quantities, right? What are the easily measurable quantities? T by thermometer, V by measuring tape, right? V can be easily measured by just measuring the dimensions, right, of the container, and alpha basically is the dimensions of the system, right? It is the dimension of the system. So V is the dimension of the system. When I talk about container, the container is the valve basically. So the system is contained inside the container, right? So V is the volume of the system, T is the temperature of the system, which is measured by thermometer, Cp can be measured by calorimeter, and alpha can be measured by altimeter. So you have now a relation between isothermal and adiabatic compressibility and with thermal expansion coefficient, volumetric thermal expansion coefficient, heat capacity, volume and temperature, right? So this is something that we can immediately appreciate, that T is positive, V is positive, Cp is positive, and alpha is positive. So in that case, kappa S is basically the adiabatic compressibility will always be less than isothermal compressibility. Now let us look at how do you use this, type of relations. You just find out which relation to apply. For example, if I tell you find the delta G, that is a change in free energy for magnesium oxide when 1 mole of magnesium oxide is heated from 25 degrees Celsius to 1027 degrees Celsius at 1 atmosphere pressure. And what we have given is the property of magnesium oxide in terms of Cp, which is 48.99 plus 3.43 10 minus 3 T minus 11.34 10 minus 5 by T square joule per mole Kelvin, right? Cp here is the molar heat capacity. S0298 is also given, which is basically the reference entropy, right? Standard entropy at 298 Kelvin or room temperature, which is given as 26.9, right? And T is equals to T plus T at degree Celsius. So T, this is absolute scale, is equals to T degree Celsius plus 273. That's we know. Now identify the variables. What are the variables? We want to find G, and we have pressure, we have temperature, right? So G as a function of Tp. We already know dG equals to minus St plus Vdp. dP equal to 0. Why? Because we are telling 1 atmosphere pressure. We are not changing the pressure. So basically the pressure is fixed at 1 atmosphere. So dG becomes equals to minus SdT. Now if I have that, now S again can be written as a function of temperature and pressure. So ds equals to del S del Tp dt, del S del Pt dP, and you can immediately see del S del Pt dP is nothing but V minus V alpha dt, and then del S del Tp is nothing but Cp by T dt. So del S del Pt is nothing but again minus del V del Tp, which is minus V alpha. So now if dP equal to 0, ds equals to Cp by T dt, right? Because we have constant pressure, right? Non-atmospheric pressure. Now you are basically finding out the change in entropy from 298 Kelvin to the temperature of interest. What is the temperature of interest? 25 degrees Celsius is 298 Kelvin, right? The lower temperature is 298 Kelvin, and this is 1027 degrees Celsius. You can multiply, add 273, so 1027 plus 273, which is 1300 Kelvin, right? So it is 1300. Pressure is 1 atmosphere and it's constant pressure. So that's why dP equal to 0. Now you can see, you can find ds, which is Cp by T dt. You can now integrate. Why you can integrate? Because you know the S0 to 98, right? You know S0 to 98 for magnesium. So basically that gives you Cp by T dt, right? 298 to T. And Cpt also you already know. Now once you know that, you get St, which is S0 to 98 plus this, and delta g is nothing but integral of dg from 298 to t, and dg is nothing but s dt, and s of t is what you have obtained. You directly use that and do but there is a, remember that there is a minus sign here. Now why minus sign? Because dg equals to minus s dt, right? So minus s dt. So you now integrate, and you basically you have an integral Cp by t here, and then S0 298, and these has to be integrated from 298 to t to get the delta z. There is another problem. So it is again coming from one exercise problem given by Diop. So, and you see again, you see what we are telling is del H del G for H and G, enthalpy and Gibbs free energy. These are basically not directly measurable quantities, but because they cannot be obtained directly from experiments, right? But you can basically measure them in terms of experimental variables. In this case, there is one variable that I will tell is may not be, but it is isoentropic. So basically, if I know the standard entropy, I can estimate the entropy, right? I can estimate the entropy, and I can also find del H del G in terms of some experimentally measurable quantities. I start with, so if I want to look at del H del G, I want to look at dH, I want to look at dG. Now dH equals du plus vdv plus vdp, which is nothing but delta q plus vdp. Now delta q is nothing but TdS for reversal process. So TdS plus, so dH equals to TdS plus vdp. That means del H del PS, right? Del H del PS is going to be equal to V, right? Del H del PS equal to V. Now you see del G, dG equals to VDP minus ST, this we have shown, and S of STP is equals to minus V alpha dP plus Cp by T dt, right? So you know ds, right? Now Cp by T dt, Cp by T dt and V alpha dP, ds equals to this, right? Cp by T dt equals to ds plus V alpha dP, right? From this relation, I can write ds plus V alpha dP equals to Cp by T dt, right? Cp by T dt. Now dt equals to Tds by Cp plus Tb alpha by Cp into dP, right? So you can get this, right? Because dt, so Tds and V alpha T by Cp, and you can see this is equal to dt. Now dg equals to Vdp minus SdT, which is basically Vdp minus S, and this dt, I instead of dt, so this is dt, I am substituting this dt here. Now if I do that, I get V minus Ts V alpha by Cp dP, and so I am just doing this calculation, and Ts by Cp ds, so del G del Ps I get as V minus Ts V alpha by Cp. You can do this little algebraic manipulation, you can basically easily arrive at this relation. So you got del G del Ps, and you have also del H del Ps. Now as you can see, del H del Gs is nothing but del H del Ps and del P del Gs, right? This is basically chain rule. So del H del P and del P del G. There, now you are using del H del P, which is basically V by del G del Ps inverse, right? This del P del Gs, right? So this is V by Vcp by Ts minus Ts V alpha by Cp, which is Cpv by Cpv minus Ts V alpha. So I can take V out, right? V is not, since V is not equal to 0, I can take the V's because V is common in all. So basically I get Cp, which is equal to Cp by Cp minus Ts alpha. If I know the isoentropic condition, that means if I know entropy value, Cp and T and alpha are all experimentally measurable quantities, right? Another thing I just quickly want to tell, that if we look at phase change problems, for example, the definition of G becomes very useful. Keeping the number of moles fixed for currently, if I look at just dG equals to Vdp minus St plus mu dn, this expression, you know del G del T with as fixed pressure and mole number of components is equal to minus S, and del G del P T is equals to V. Now as you can see, if I write G, if I have so these are schematics, okay? So G, if I write or express as a function of T, the slope has to be minus S. where S is positive, right? S is positive, is the entropy. And for gases have will have a very large entropy, right? Because the molecules are far apart. They can be arranged more randomly, so the randomness is more in gases. Liquid has little more order, but still the molecules can move around. Liquid has more order than gas. Gas has almost no order. And then you have solid where all the atoms are very closely packed, right, in solids. So as a result, it's like you can assume like some springs are connected between these spheres, right? If you think of, and this has a much regular pattern. Solid has a much regular pattern than liquid. So in general, solid has the lowest entropy, and liquid has slightly higher entropy than that of solid. But in the gas case, it is very, very large. And as you can see, as you increase temperature, the randomness basically increases. So temperature, again, as I wanted to tell you, temperature and entropy are conjugate variables. So if you increase temperature, the entropy goes higher. So minus S, that means, tells me that gases will have free energies which will have a very steep slope of minus S. For liquids, it will not be as steep with temperature. For solids, there will be very little change in slope, right? Means minus S, because S itself is small for solids compared to that of gases. However, now if I look at volume, del G del P, which is at a fixed temperature, you get V, right? Now volume, obviously, gases will have a very large volume change, right, as a function of pressure. So for gases, you can see how dramatically the free energy changes. On the other hand, for liquids and solids, the change is very, very small. Now, this is something that we would like to emphasize, right? These are very schematic diagrams, but see, for phase shift problems, the trends basically become very evident just by looking at the slopes like del G del T or del G del P, right? So, one very useful relation that I can think of is the Gibbs-Helmholtz relation, which is G. Again, we know G equals to H minus Ts. From there, we can write S, which is H minus G by T, and del G del T P equal to minus S, which is basically G minus H by T. Now, if I do the differentiation, del T of D by T, I get 1 by T del G del T P, and G del T of 1 by T, which is minus G by T square. Now, I take 1 by T common, and I get del G del T P minus G by T, which is G minus H by T by G minus G by T, which is basically coming out to be minus H by T square. You will see that this becomes a very, very useful relation, particularly when we have phase change problems. So, this is the phase change problems we will deal with in the next week of lecture, and you will see that for phase change, this type of relation becomes very useful. Del T of delta G by T, which is equal to minus delta H by T square, right? If I know the delta H. And we will also look at in the next week the connection between microscopic world of the microscopic world of atoms, right? The macroscopic thermodynamics we are looking at macroscopic variables like volume, temperature, pressure, and all. But there is this microscopic world, and I have talked about, say, some molecular interpretation, for example, is what we will be talking about. Molecular interpretation of energy is already something that we have given. Molecular interpretation of temperature is also something that we have given, or heat capacity. Now we will try to find out the connection between entropy defined in macroscopic thermodynamics and the entropy that you can realize in the microscopic world. So we will try to do that or discuss that in the next class, right? Next class in the next week, like week 5. Okay then. Thank you very much. And another thing, before I end this lecture, I would like to tell you that, see, when I am recording for NPTEL lectures, in general, it might be possible that I am going a little bit faster, right? Because we do not have a live interaction with the students here. So as a result, I might be going a bit faster, and sometimes concepts, if I go fast, you may not be able to understand very clearly. So as a result, if you have any doubt, if you can somehow post comments and let me know, I would take up these problems in my subsequent lectures. Thank you very much for your attention.